Hi guys, thank you so much for attending our talk today at Big Mountain Data and Dev. My name is Erica. I am from GS. I've been here for 8 months now, and I work in the product data quality department, which involves a lot of verifying and verifying and making sure that data is valid, as well as pricing sources. So I'm going to hand it over to Roshni to introduce herself and start off our talk today.
A very good morning to all. Thank you so much for taking time out and attending our talk today. My name is Roshni Chatterjee, and I've been with the firm for 3.5 years. I've been with the consumer and investment management team. So Erica and I will be presenting to you today machine learning and log analytics. Our slides are going to be for 30 minutes, post which we will open it up for Q&A. So machine learning has become such an integral part of our day-to-day lives. Right from get-go, with every little thing that we do, machine learning plays such a big part at the back, and we don't even know about it. Right from a higher level where commercial airlines rely on autopilot feature to a lower level where we have self-driving cars and vacuums that clean the houses by themselves, machine learning has become truly indispensable. And hence, it's becoming increasingly important to understand the application of machine learning in businesses. To drive this point home, let's talk about one widely used application of machine learning, Google. Why do we Google something? Easy, right? We Google something to get the most relevant web pages. But how does Google determine what's the most relevant web page? That's where machine learning comes into picture. So what is this buzzword that everyone's talking about? Machine learning is the way a machine learns by analyzing data, finding patterns and trends, learning from previous experiences, and making prediction with minimal human intervention. The key point to note here is that we need to minimize human intervention. At the same time, you have to maintain the same level of accuracy and performance. So to do that, you have to build a system that's intelligent enough by feeding it abundant data so that once a new input is fed to it, it's able to make a good prediction. Machine learning is an iterative process. It's a constant learning process. So just like humans, right? So when humans have a decision to make, they look at their previous experiences in order to make a decision. Likewise, machines learn from existing data, make prediction on new input, calculate accuracy. So if you're happy with the outcome of your learning, then you know your model is well built. But if there's a very big variance or you're not happy with what you're getting, that's where you know you have to fine-tune your model and your machine has to learn again. The more your machine undergoes learning and training, the better prediction it's able to make. So who's using machine learning these days? Retail and entertainment. As we all have seen, and especially now during the pandemic, Netflix, when you're looking to watch something over Netflix, if you look up for something, say an action-packed genre, and the next thing you open Netflix and see, you will definitely be recommended similar shows. And likewise for Amazon, if you're looking to buy something, the next time you open Amazon, you'll be suggested similar products. Price optimization and marketing strategies. So the prices of goods fall or rise based on certain price optimizations that Amazon puts in. And this is to maximize profitability. Financial institutions like banks, they're using machine learning to detect fraud. So if there's a fraudulent customer who's making a transaction, say a really big transaction that they've not done before, the bank will promptly send you a statement asking that transaction has been made by you. Model-driven trading. So a lot of financial companies are using latest announcements about companies, the revenue results of that quarter in order to derive fall and rise in stock prices. It's being used by the government to save money and to minimize identity theft. Aviation. So we've all faced that in the months of November and December, the holiday seasons, the prices of tickets spike up. Healthcare. Doctors are using machine learning today to help detect red flags that help them with better diagnosis. So what is the one common thing amongst all of this? It is that everyone's online today, whether it's watching something on Netflix or doing a bank transaction or just simply surfing the net. With everyone being online, this generates a humongous amount of data per minute. Hence, it's becoming increasingly important to analyze this data properly to facilitate dramatic innovations in all sectors, public, private. So now that you know a little bit about machine learning, let's talk about the learning process. The foundation of machine learning is the raw data, the data that's fed to your model. This data could be stored in databases, SQL, NoSQL, text files, Excel sheets. The focus here is on density, variety, and volume. So along with having a lot of data, it's also important to have a good mix of data in order to make better predictions. Now, this data cannot be fed to your model as it is. It has to undergo some cleaning because there's a lot of noise in data, and this tends to distort prediction. So it's important to retain useful information, eliminate noise, eliminate outliers, and impute missing data points. Cleaning can be done using feature engineering, normalizing, splitting. Once your data has been cleaned, it can be split into test data and training data. The next step is one of the most crucial steps because this is where your machine undergoes learning. It learns based on the training data that's fed to it. And this is where you need to decide what algorithm will be running at the back of the scene. Once your machine has undergone tremendous amount of training and learning, that's where you feed it the testing data in order for it to make a prediction. This is where you calculate the performance and accuracy of your prediction. And finally, the last step is one of the most important steps because this is the decision-making step. If you're happy with the outcome of your prediction, you know that your model is a good model. But if the prediction is not really close to what's the expected output, that's where you know that you have to treat this. You have to fine-tune your model, maybe treat missing values, introducing some new features, or hyperparameter tuning. So now that we understand the process of machine learning, let's go back to our main example, Google. So let's say you start with how to start with machine learning. One thing worth noting is that when you search for something, Google is not really going to the World Wide Web real time and finding this result. Because there are billions of web pages out there, it's very difficult and very tedious and time consuming for Google to go and find all of this real time. So what Google has done before is that it has introduced some programs called as spiders that crawl the web, index the web pages, and adds them to a master repository. This could be around 1 billion to around 1 trillion results. Finally, when you're searching for something, Google picks up the keywords and goes and searches against this index. So say your search, how, start, machine learning, these words are matched against the indexed pages that's already present. And they're matched using page titles. They're matched on the headers, body, backlink. This could further narrow down your search to say 1 million search results. But are we happy with that? Do we still get the most optimized result? Maybe not. So that's where a ranking engine comes into play. The ranking engine basically assigns a threshold based on some factors like sequence of ordering. So how to start with machine learning, if that appears in the same order in some of the web pages, we know that those web pages are more relevant than the others. The TF-IDF value, which means that giving words like machine learning more priority than stop words like how, to, start, and frequency of user clicks. Based on this, a threshold is assigned, and based on this threshold, you're able to see the most relevant outcomes. Now, every now and then, some data engineers, they go and recalculate this threshold, they fine-tune this threshold. So something as easy as just looking up something on Google has a lot going on behind the scene. Now let's jump into some different learning models. Machine learning models are divided into supervised, unsupervised, semi-supervised, and reinforcement learning. But for this presentation, we'll be focusing on supervised and unsupervised. Supervised learning, as the name suggests, the training data is labeled. It is used when there's a well-defined question at hand. Is the email spam or not a spam? Is it going to rain today? The broad categorizations are classification and regression. Now let's take the example of the email. Say you have a data set that consists of a lot of emails, and within that email, the sender of the email, the subject line of the email, the body of the email, this is all labeled data. Now your machine knows that based on this label, it's able to predict any new email coming to the server. So let's say the subject line has a lot of exclamation marks and it's all in caps. Your machine is able to say that, okay, this is not from an authorized sender. Let's classify this as a spam. Unsupervised learning is quite the opposite of supervised learning. The training set is unlabeled. Unsupervised learning is uncovering hidden patterns in unlabeled data by reducing large data sets to smaller clusters. Some good examples are customer segmentation to improve marketing strategies and recommender system where you suggest a few groups, similar content, people who view similar content together, you suggest them similar items to view. And the broad categorizations are clustering and association. Clustering is basically forming natural groups. So let's take an example of people who go to Walmart and they want to buy bread. That's clustering. And association is using clustering to derive some associative facts. So people who want to buy bread also want to buy eggs. That's association. So as we discussed in the previous slide, we have two broad categorizations of supervised learning. So classification is used when the prediction is a discrete valued output. So let's take an example of where a student has written an exam and you want to determine whether the student has passed or failed. That's where you use a classification model. Pass, fail, yes, no, rainy, sunny. Regression is used when your result is a continuous valued output. So if you want to predict what's the percentage your student has gained in an exam, that's where you use a regression model. Some popular models are naive Bayes, k-nearest neighbors, support vector machine, random forest, and neural networks. So as we saw in the previous slide, unsupervised learning tries to find hidden patterns in unlabeled data. Clustering is a very good example of unsupervised learning, and within that, k-means is a very popular algorithm. So as you can see in this picture, there are a lot of data points that's unclustered. They don't have a class assigned to it. In k-means, the first step is to assign a value of k. So for our example, we will use k equal to 2. Now, as you can see, there are 2 points assigned. One is the blue point and one is the red point. The blue point is called, these points are called center points or centroids. So the other data points that's closest to the center point is assigned that particular class, whereas the red points that's closest to this red star are assigned to the red class. But is this the best clustering that we can do? Maybe not. So that's where you have to recalculate the center point. We move the position of the center point and recalculate the data points that has to surround these center points. And finally, you can see that there's another cluster formed. Is this the best you can do? Well, let's see. We changed the value of the center points again, and we've seen that the clusters have not changed as much. That's where we know that this is a good stopping point. Finally, you all must be wondering, what's a good algorithm to have? Well, there is no secret formula to this. You have to perform trial and error methods and calculate your accuracy and then determine what suits your use case the best. But a key thing to remember is that define your problem statement well, analyze the data well, make sure there's no missing data points, choose your algorithm wisely, check the accuracy of your output, and optimize. With that, I'll be handing it over to Erica to continue with the application of machine learning.
Thank you so much, Roshni, for that wonderful background on machine learning. And now that we've seen a little bit behind the scenes and how machine learning works, essentially, I'm going to give a very led example on one specific application in the realm of data engineering. So One specific example that I'd like to talk about involves a problem statement. And the problem statement is that we as engineers run a lot of jobs, run a lot of batch jobs. We have a lot of lines of code. So what happens if our batch job fails and we're not sure why, and we need to dig around in those lines after they fail? Is there a way to make this more efficient? So let's take a look at some questions to help us better understand this problem so that we can break down and solve it together. In the scope of data engineering, which is in this batch job example, what is a useful indicator that we can use to predict an error before it happens? Here, it's going to be text words and phrases in all of our chats, in all of our log files generated by these batch jobs, in system reports, and various other places that we store all of our data. So as these files are generated, are there words that come up frequently before an error occurs? Are there words like capacity, invalid, error, all of these other things that you see that come up in red text when your batch job failed? If we have those, is there some way to determine which application or endpoint is likely to fail if specific words appear? So if capacity appears, is there a specific endpoint or batch job that we know will fail? For this, we like to try and use text markers to predict these short-term outcomes. So to break down our problem in the realm of text mining, I'm going to give you 4 kind of quadrants of problems, so smaller bite-sized problems, 4 ideas that we're going to look at to kind of solve this batch job problem. The first one is going to be scale. How many lines of code, how many servers, devices, and storage do we have to sort through? So I think, for example, Goldman has over 300,000 servers and 90,000 databases. We also have the data lake. So that's a lot of stuff to dig through. So this is a huge problem. The second is association. Are there words that occur frequently across multiple teams and batch jobs? Do they occur in messages as well as batches? Do they occur somewhere else? Do they occur at endpoints? The third is going to be tagging. Are there words and patterns that we can give a specific tag and give that tag an importance? So is this one more important than another when you see it come up in your log files? The final one will be flagging. Can we catch these words that we've designated as important in real time in such a way that will allow us to create alert systems that will let us know before our batch job fails that it's going to fail? So again, for this, we're going to look at text mining, and I'm going to give you a little bit of a motivation, because you can say, it's not that bad, it fails. I'll sit here, I'll look through the log files, and I can write a code to find specific patterns for me. That's well and good, but that's post-processing. So here's a few motivations for us to use machine learning to kind of prevent those, time spent later. The first one is going to be the fact that the problem space is defined differently. So if you sit there and say, I can write a code for all of the log files that exist already, that's cool, but that's response driven. Your batch job will still fail. With machine learning, if we can create an alert system, that will lead us to a problem driven or alert driven approach, which means that before your job ever fails, you'll know about it and we can try and fix it, or we can even know what the problem is and we can fix it. So that will save us a lot of time, energy, risk, a human risk writing that code, and just the volume of batch jobs that have to be run. Finally, or not finally, but another good point is that there are specific patterns, as I mentioned, across multiple different platforms and across different teams. You as a specific engineer sitting in one division, Roshni and I sit in different divisions, but what if we run similar batch jobs that have similar key phrases? A machine can learn from both of us and be twice as efficient as each of us communicating independently. Finally, and importantly, a reduced backlog of breaks, which I think everyone can agree is a very good thing. So what does our timeline look like right now without machine learning? I run a batch job. What happens? There are 2 outcomes, success and failure. That's about it. I mean, maybe there's more, but there's really success and failure. What happens if it's a success? Wonderful. We love success. What happens if it's a failure? This is what I mean by a post-event processing. If there's a failure in your batch job, you as an engineer are going to sit there and look through all of the log files, spend your time trying to find the error that caused this specific failure, and there's some risk involved. If you catch the wrong line, if you dig through legacy code and you maybe tweak something that shouldn't have been tweaked, that's some risk there involved. If you can get through all of that, wonderful, that leads to your success. However, let's look at what a timeline could look like if we implement machine learning. So log files from past runs, which are generated from batch jobs, including failure patterns, can all be used as kind of our input for the machine to learn off of. So Roshni mentioned this when she was saying, you know, we need to generate a lot of data. This is a lot of data. I know that we run 20 or so batch jobs a day in just my team. So that's a lot of log input for our machine to learn off of. So as we generate these batch jobs, as we generate potential failure patterns, and as we generate log files, that will all be our input. Now, when you run the batch job, there's still only two outcomes, success and failure. But once we have a machine that has learned off of all our input from failure patterns and log files, we can actually create a preemptive third alternate. And that is, as a failure pattern occurs in your batch job, before it either reaches success or failure output, we can have an alert, which means that we get rid of the entire failure branch of this process. We either will have a success or an alert, and our failure will be prevented by letting us know that by having that alert come up to us and say that, hey, your job might fail. Why don't you go take a look at this now instead of 5 hours from now when it finally does fail? So this is a really much more efficient way of kind of tagging those errors for ourselves. How would a machine that's learning do this? I've created this kind of like flow for us to look at. So how will we catch these phrases to send the alerts? How do we implement this with machine learning? Say you have one log line and it says that your connection to port 45 has failed, the connection has failed. That's great. We know that that's a very specific error. That's a pretty good one to hold on to, but it's a single line. And as mentioned before, we need a lot of data for us to train off of. So all of those huge inputs, all of those like millions of lines of log are going to be that preclude a failure specifically are going to be our input. And we're going to look at all of the patterns that are found in all of the log files. So for example, here we see that the connection to port X has failed, the connection has failed. It doesn't matter which port it is, we see that there are key phrases inside these log lines that allow us to recognize a pattern. So the machine will learn, it will recognize these phrases and assign them importance and tag them as key phrases. So in this third row, you see that I just replaced connect to port as a key 25 and failed as key 1 for our machine that's learned. If we can recognize these errors, we can produce alerts or set up alerts for the engineers to receive before our failure. Okay, that all sounds great. What if you have a phrase that doesn't specifically associate to a failure? Let's take a step back. How do we tag these phrases specifically? So in a really wonderful, easy example, one key phrase, like the word failure, is going to associate to one single event or failure. That's awesome. That's a specific association. The machine will find this very easy to learn, to tag, and to create an alert. So we'll call this we'll call this a specific association, and we can automatically use this as a learned association in our machine. That's going to come very easily. What happens if a key phrase precludes 3 different, 4 different, 5 different events or failures? Maybe it precludes an event in one system and a failure in another one. How will we know, and how will the machine know to learn what the outcome should be? So these are called non-specific associations. These will actually require feedback from someone who has a lot of knowledge and works closely on these batch jobs to give the machine feedback on whether or not these key phrases are useful for an alert. So we're going to have some human feedback here, tagging potentially, oh, the word critical is not actually something that precludes a failure in many events, but sometimes it does. Events that happen infrequently, but are very severe, can also be tagged by humans so that we can help the machine learn, because those will be rare instances, but we really want to make sure that we catch them so we can reinforce that learning in that way. So we've talked a little bit about how the machine is going to use this. And I've mentioned that we mentioned that it takes a lot of data to do it. So I just wanted to outline some costs and benefits, or challenges and benefits, of implementing this potential timeline. So the challenges certainly include the computation, the expense of computation. If there are 1,000 patterns that you have tagged in your machine, and we have 1 billion log lines, that gives us 10 to the 12 matching operations to work through. So it's a lot of it's computationally expensive, but if you have enough storage and enough, memory, then the machine should be able to work through it, but it's going to be a little bit of work there. You may also need experts from the field for retraining and reinforcement, as mentioned on our last slide, to make sure that those non-specific associations are tagged and really taken care of. You still have to rerun your field batch jobs, unfortunately for now, as you're training the machine, just to make sure that, you did run a failed batch job. You're gonna have to run it so that it goes through to success. And finally, storage. So the large amount of input data needs to sit somewhere, so that's going to be a challenge as well. But if we can surmount all of those, there are a lot of benefits to implementing this machine learning timeline. Again, this is alert centric. So precluding the event failure, you can have an alert that will let you know that your batch job is going to fail. This will reduce time and effort involved in those failed batch jobs. As well, machine learning will take the brunt of the work away from us as engineers. So those billion, 10 to the 12 matching operations, that's not something that we need to sit through and figure out. This machine will do all of the work, most of the work for us. So we can focus on improvements and other pieces to this process. Finally, I just want to mention that the error threshold is adjustable. And what I mean by that is saying, if you think that your machine is throwing too many alerts or too little alerts for specific phrases, you can adjust that threshold and retrain it and say, this one we don't feel is very important, please throw us less errors. Always say please to the machines, but please throw us less errors, things like that. So you kind of have an adjustable threshold to how your machine has learned. Awesome, so we hope that you implement this. But the benefits of using machine learning on a larger scale, I just want to touch on and recap there. Current applications in financial engineering include everything from chatbots, like Bank of America's Erica's app, to fraud detection, which we've talked about. If you make a suspicious purchase, your credit card will ping you, credit evaluation, and long-term deep portfolios that require no human intervention in them. Outside of financial engineering, machine learning is being used for a plethora of things. We're looking at risk and patience using megadata, natural language processing, a bunch more things, including edge detection for pictures, self-driving cars, and artificial synapses in chemistry. With that, I'd like to conclude our talk. We would love to take questions both through the Slack channel and on, what is that one on Loud Swarm called? So Casey will read your questions out as they come. And we thank you so much for coming to our talk. We really appreciate you guys coming to take your time and listen, and hope you've been enjoying today's event so far. Please leave feedback for us if you feel that we did a particularly good job or just in general. And thank you from us.